Our project title is Solar PV and Grid Based Non-Isolated Converter for Plug-in Electric Vehicles. Our batch members are Divyadashini, Sonali and Shivasri. Objective of the program: Introduction, Lecture Survey, Existing System, Problem Identification, Proposed System, Results and Discussion, Conclusion and Future Work Reference. Objective of the project: the objective of this paper is to design and implement a solar photovoltaic grid-based isolated converter for plug-in electric vehicles. The proposed converters is model estimated and tested. The two converters are used in this. One is buck boost converter and another one is SEPIC converter. This is the existing system which we use buck boost converter. So we have a rectifier, a transformer 12 volt, power supply of 5 volt, a controller, a driver circuit and load. In this block diagram we have buck boost converter. On using buck boost converter we have drawbacks in charging capacity of the vehicle, so we use SEPIC converter. Buck boost converter is a type of DC to DC converter that features both buck and boost converter. The main disadvantage of buck boost converter is bidirectional converter. It has a low power factor. Due to lack of low power factor correction, we use a SEPIC converter. SEPIC converter over buck boost converter. SEPIC converter are more efficient than buck boost converter as they are able to step up or step down the input voltage while keeping current flow in same direction.
As mentioned before, Shivasri has been explaining about the existing system of a project. So now I'm gonna explain about the working principle of a proposed system. And as we have mentioned earlier, the proposed system consists of two modes of inputs, that is a solar panel and another one is a grid. Solar panel, which is known as an SPV, solar photovoltaic, and another one is grid. So in the slide shown, it is given the structure of the proposed power electronics interface, PEI, which is the proposed circuit diagram of a project. So yeah, you can clearly see that PVC panel and grid are attached to the circuit, and then from PV panel the current and voltage, that is goes to the inductor L1, and from L1 then it goes to the capacitor when switch is on, and then it goes to the magnetic inductance where it stores magnetic energy and it converted it into magnetic energy. Then it goes to the capacitor, and then it goes to the battery voltage, and then it goes to the CVH. Then we can at last it goes to the battery. From the battery we can run a motor. So as per the modes of operations, SEPIC mode of operation consists of two types. One is a PIC mode. From the PIC mode, you can clearly see that we have given two pictures. First one is when the switch is on. In this mode, PIC mode is known as a plug-in charging. Only the battery is charged through the grid. So there is no involvement of the solar panel here. So battery load, we can clearly see that when the switch is off, from the magnetic inductance of LM and it transfers to CB, then the circuit is circuit of the current flow is operated. So this is known as PAC mode, and followed by this PAC mode we have SPV mode. In this mode the circuit is charged. I mean, like input has been given by the solar photovoltaic, which is known as a solar panel, in which this current and this voltage has been given from the panel. As we all know, the solar energy will not be the same as constant depending on the sun's UV rays. So we will be using a rectifier. So rectifier and a controller, so it will remains constant, which prevents fluctuation in the circuit. So yeah, it is in the SPV mode, it is same as the PIC mode. Only the difference will be the grid will be deactivated, the battery is charged to the SPV system, and it is operated in a non-isolated SEPIC mode. And here we will be conducting an MPPT. MPPT is also known as a maximum power point tracking. Maximum power point tracking is a technique used with the variable power sources to magnetize energy extraction as condition vary. The technique is most commonly used in the photovoltaic systems, but cannot be used in the wind turbines or in the thermophotovoltaics, but it is commonly used in the solar panels, I mean, like photovoltaic. So then we have flyback operation. In flyback operation, here also we have two modes of operation, that is PV mode and RV mode. PV mode is known as propulsion mode, RV mode is known as regenerative braking. PV mode, in the slide shown, in PP mode, when the switch S2 is on, the magnetizing inductance LM of the high frequency transformer stores the energy, and current flows through the from the LM. It is indicated in the blue line, and the current flows through the LM, and then it is goes to the capacitor, and then it goes to the battery, and charging is taking place. This is happening during PP mode, and then when S2 is off, the LM transforms the stored energy from the CVH. In the circuit diagram, CVH, our block diagram of a proposed system. In this block diagram, we have a PV panel, and from the PV panel, we will be the voltage or current will be flowing to the SPV converter, and then it goes to the battery. From the solar panel, we will be using an as I said before, we will be using a controller and a rectifier. So yeah, we will be using a controller and a TLP250 driver circuit, which will be converting the AC supply to DC supply. And as we all know, SPV converter is a DC to DC converter. So from the SPV converter, it is given to the battery, and from the transformer, that is to the grid voltage of 12 volt, and then we will be giving the power supply of 5 volt. So yeah, then from the transformer it will be go on to the controller, and it will be rectified, then it goes to the SPV converter, then SPV converter, then to the battery. This is our block diagram. And then in the results and discussion, we have a boost converter simulation process. As we have said earlier, we are going to compare both the existing system and the proposed system. So yeah, so we have the simulation of a buck boost converter. In this simulation result, we have given 12 volts of input, but we are getting about of a minus 5 to minus 6, and the output has been constantly fluctuated, and we can't take a single value. So by using the buck boost converter, we can't get an accurate voltage, and the efficiency will not be great. And then as we are using the buck boost converter, we will be having more number of components, so the cost will be high. So yeah, as I said before, this is our block diagram of the CPIC converter simulation part. We have been using grid and solar, and then rectifier, and then CPIC converter, then CPIC converter, the DC, deep DC. This is about solar PV. Shown in the circuit diagram, we will be giving both current and voltage. So this is about solar PV current, and then we have solar PV voltage. And then we will be moving on to the propulsion and regenerative braking. And during propulsion mode, the motor will be running. So as the motor will be running, it will be like from the start, and it will goes to the peak. And in the regenerative braking, it will be in the reverse operation. From peak, it will goes to the lower part. So that is has been given in this PPT of a propulsion and regenerative braking. So yeah, this is the overall input and output voltage of a voltage simulation. In this we have given 200 volt voltage, and we will be getting about 250 voltage. But as I said earlier, in the buck boost converter, I have given 12 voltage, but we got the output of around minus 5 to 6, so it will be not efficient to be used in an electric vehicle. So and we have given the comparison tabular column of buck boost converter and CPIC converter for the inductor and capacitor values. Then we have our experimental setup, which will be our hardware setup. And this setup we have CPIC as a transformer, microcontroller, and TLP250 circuit driver, driver circuit, and CPIC converter. Here, as for the solar panel, we can't afford such a big future work. In this paper, we have a multifunctional PEI as proposed on the on-board application, and the proposed PEI works effectively in all the vehicular modes, and the reliability of this converter is so high, and the cost of this converter is also low when we compare to the existing system, because the buck boost converter consists of two converters, buck and boost, and the components will be more and the cost will be high. The efficiency will be low, so we have so many disadvantages.